In this particular video, I'm going to discuss about the conformational structures of cyclohexane. This topic is from degree first semester syllabus, that is Alicyclic hydrocarbons chapter 6. The whole chapter has been discussed on my YouTube channel, and the details of this has been given in the description box below. So if you like it, please do like, share and subscribe my channel. See, if you look at this cyclohexane structure, and it's a very prominent member of the cycloalkanes, the cyclohexane, and its conformations will and stereochemistry will play a very important role in the reactivity. So it's necessary to know the conformational structures. So if you look at this internal angle of this, it's 120 degrees. I mean, if the ring were to be planar, if this cyclohexane structure is to be, if you assume that it's a planar, flat, and then the internal angle is 120 degrees, 120 degrees. And if this 120 degrees, it would suffer from certain strain which is called as an angle strain. So I've already discussed this in my previous video about the Bayer strain. I repeat, if it says that if any system which is having the sp3 hybridization, if it sp3 hybridization, then the angle would be, that means 109.28, and that which is known as an ideal angle or a tetrahedral angle. So if any molecule which is having this sp3 hybridization, if the angle is more or less than this ideal angle, that is 109.5, will suffer from certain amount of strain which is called as an angle strain, because it is deviating from that angle, that is 109.5 degrees. Now if you assume that the cyclohexane is planar, then the angle is 120 degrees, so it will suffer, if it will definitely suffer from this angle strain. And one more thing, if the molecule is planar and all the hydrogens on these adjacent carbon atoms, that means on this vicinal hydrogen atoms, then they will be in eclipsed conformation. That means all the hydrogens will be on the adjacent carbon atoms, will be one behind the another, and they will be in eclipsed conformation and not in stagger, so will be suffer from torsional strain. So if the molecule were to be planar, it will suffer from two types of strain, that is, one is angle strain and the other one is the torsional strain. So but when we look at these heats of combustion values carefully, and from these heats of combustion value data, the cyclohexane is suffering from zero angle strain here. See, so when you look at this heat of combustion value per CH2, per CH2 in kilojoules per mole, it is 654 kilojoules per mole, and this is for a unstrained straight chain alkane. The value is around 1654 kilojoules per mole per CH2. So it is the same as per CH2, so kilojoules per mole. This is the same as per unstrained CH2, I mean long chain alkane. So this is not suffering from any strain, that is the angle strain or the total strain or the ring strain is zero. So when you look at these heats of combustion values, it clearly says that the molecule is not suffering from any kind of strain, because according to the experimental value, it is suffering from zero strain. So the molecule is not planar. It clearly suggests that the molecule is not planar, or some other conformation is adopting, that is warped or puckered conformation, uh, where it is free from the strain energy. So in reality, when you see this, the cyclohexane molecule is adopting this puckered chair conformation, and it is the more stable conformation of all the conformations of cyclohexane. Yes, when you look at this, why it is so stable means this chair conformation, because it is free from angle strain. The angle is normal tetrahedral angle or the ideal angle, that is 1.5 degrees. So it's free from angle strain and also free from torsional strain because all the hydrogens on the adjacent carbon atoms are in staggered conformation and not in eclipse. That means these hydrogens are not one behind another. So it is not suffering from torsional strain too. And the one more strain is the van der Waals strain, where the hydrogens on these carbon atoms are not crowding. So there is no crowding here. So this free from no crowding between the hydrogens here. So it is free from this van der Waals strain because it is free from all three kinds of strain, that is angle strain, torsional strain and van der Waals strain. This chair conformation is the stable of all the conformations of this cyclohexane, and it lies at the energy minimum in the potential energy diagram. So if in the potential energy diagram this lies at the minimum energy, that is the lowest energy, this chain conformation is uh, yes, so it is in the minimum energy. In the potential energy diagram, this is lying at the minimum energy. So this particular chair conformation is called as the conformational isomer, or simply the conformer, because it is lying at the minimum energy in the potential energy diagram. So this is what is about the chair conformation of cyclohexanes, and this diagrams reveal it better about the chair. So it is totally chair, so it's a comfortable chair here. So this chair conformation, and all the hydrogens on all the carbon atoms are in staggered conformation and free from angle strain and also van der Waals strain. So this Newman projection formula, when you clearly observe these hydrogens, see these are all in a staggered conformation and not in see this hydrogen. So the not in eclipse conformation, so it is free from all kinds of strains. So one more conformation of the cyclohexane is the boat conformation, or the boat form, where by just flipping the left side of this chair we can obtain this boat form. So this phenomenon where one chair can be interconverted into an another, or this converted into an another through another conformation, or like boat or any other conformation, is called as just a chair flipping or ring flipping. So by means of flipping of the chair, so one chair conformation can be converted into another chair conformation. This type of phenomenon, or this phenomenon, is called as an ring flipping, or simply the chair flipping. And when you look at the types of the strains in this board conformation, so it is free from angle strain, okay, because so I write one by one here. This angle strain, there is zero angle strain because the bond angle is 109.28, so it is free from angle strain. So but when you look at this torsional strain here, yeah, it's suffering from little amount of this torsional strain, because when you observe this, the hydrogens on C5, C6 and C2, C3 hydrogens, they are eclipsed. See, so hydrogens on these two are eclipsed. When we observe this, hydrogens on C5, C6, C2, C3 are eclipsed. You can see this clearly here. So here it is C2, C3 hydrogens, and here it is C5. Yes, C5 and C6 hydrogens are getting eclipsed. So there is a torsional strain because of eclipsing of hydrogens on what? C2, C3 and C5 and C6. Yes. And because of this eclipsing, what will happen is the hydrogens on C1 and C4 are coming close to each other. So they are, because of this, eclipsing these forces, these hydrogen atoms on C1 and C2 to interfere with each other. So these are pointing upwards on the boat, like the flagpoles are called as flagpole hydrogens. These two hydrogens are called as flagpole hydrogens because these two hydrogens are pointing upwards from the ends of the boat like two flagpoles. And there's a crowding in between these two hydrogen atoms. So Yeah, you can show this crowding in this diagram here. When you see this here, yeah, these two hydrogens, so this C1 and C4, right? Yeah, C1 and C4, the flagpole hydrogens, the distance in between these two is around 2.5 angstroms. So there are only 2.5, should be 2.5 angstroms, but it's only 1.83 angstroms. So that is lesser than the sum of their van der Waals radii, that is 1.83. So it is suffering from this van der Waals strain. So what is this van der Waals strain? Is this arising because of the crowding of the hydrogens, or the distance in between the hydrogens is less than that of their sum of the van der Waals radii. And when we observe this here, the distance in between these two hydrogens is only 1.83 angstroms. It is less than that of the sum of their van der Waals radii, that is 2.5. So because it is less than that of the sum of their van der Waals radii, that is 1.83, it is suffering from this van der Waals strain too. So this boat form now is suffering from here van der Waals strain too, because of the crowding of these flagpole hydrogens. Because of the distance in between these flagpole hydrogens is only 1.83 angstroms apart, it should be around 2.5. That is the sum of their van der Waals radii. So this particular one is suffering from torsional strain and van der Waals strain, although it is free from this angle strain. And because of this, it lies, I mean, the energy of this boat form is more than that. Where is this? Yeah, boat form is more than that of this chair form. The energy of this by how many kilocalories? Means around 7.1 kilocalories per mole. So this is in the lies, I mean, this is more in energy than that of the chair form by 7.1 kilocalories per mole. And because this is lying at the energy maximum in a potential energy diagram, so I've already told you this in the potential energy diagram, it lies at the energy maximum. So this is not a conformer, this is only a transition state. So this boat conformation is only a transition state because it is in the energy maximum in the potential energy diagram. So yes, and yes, so because of this, in order to relieve from certain this strain, what happens in this boat is it's slightly twisted. The obtained, I mean, the twist boat conformation, it will acquire one more conformation, that is a twist boat conformation, by slightly twisting it. Uh, boat conformation. Then the twist boat conformation is formed, where this C2 and C3 and C6 move down, that carbon atoms, C2 and C5 carbon atoms move up, and I mean C3, C6 go down, C2 and C5 carbon atoms go up, and flagpole hydrogens move apart from each other. So these two hydrogens will move apart from each other in order to relieve from this eclipsing strain, I mean the torsional strain, and also this van der Waals strain. So that's certain amount of strain it is getting relief from, so that the eclipsing of bonds is reduced. So this is what is the twist boat. And the energy of this twist boat is lower in energy than the boat. Okay, but it is a twist boat is more in energy than that of the chair by how many kilocalories? This is around 0.5 kilocalories per mole. So according to this, twist boat is more in energy than chair, and boat is more than the twist boat. So boat form is the at the energy maximum, and chair form is the energy minimum in the potential energy diagram. Yes, and the energy difference in between these two is around 7.1 kilocalories per mole. Yes. Mm, yes. And Yes. 23. This is nothing but 5.5. Yes. Yes. This is 5.5 kilocalories per mole. Yeah, this in this diagram it can be clearly understood. If you see this uh, in the boat conformation, the flagpole hydrogens are facing this van der Waals strain, but in this they are moved apart by slightly twisting the boat flagpole hydrogens, and the distance in between these two C2, what is that, C2 3 2 and 3, and also 5 and 6. Yes, these hydrogens are little relieved from this eclipsing strain, these carbon atoms, because of the twist boat conformation. Slightly twisting the boat will get the twist boat conformation. So when you look at these conformations, this is the chair form, this is the boat conformation, which is the energy maximum, then the twist boat, this is more energy, and then comes this half chair conformation. So this half chair is at the more in energy. Yes. So chair conformation is the most stable of all of them, uh, of all the conformations, and both conformations is least stable than the chair conformation. Yes. When we look at this potential energy diagram, we can clearly understand all this. This is a chair conformation. This is the half chair. So one chair can be converted into another chair by means of these transition state, where we'll first get into the half chair form, where this is slightly twisted like this, moved, then comes this twist boat, then comes this boat where, yes, moving up, and where this again, this carbon atom, that is fourth carbon atom, is slightly moved, and then comes this half chair, another half chair, where this is moved down here to get this chair conformation. So one chair can be converted into another chair, and this conversion is nothing but the ring flipping or the chair flipping, where the fourth carbon atom here is coming down, and this one carbon atom here, it is down, is moving up here. When you look at the energies of this, so this is 7.1. Yes. And the energy of which is lying at the energy minimum in the potential energy diagram, the conformation is the chair conformation, and this boat is more in energy when compared to that of the chair by 7.1 kilocalories per mole, and the twist boat is more in energy than that of this chair conformation by uh, 5.5 kilocalories per mole. And these two half chairs are nothing but the enantiomers, because they are the non-superimposable mirror images. They are the mirror images which are non-superimposable. So these two are the uh, enantiomers here. Yes, and the energy difference in between the chair form and the boat form is 10 kilocalories per mole. So the chair form is more stable or stabilized when compared to that of the boat form by 10 kilocalories per mole. So this is what is about the